Hi, I'm Ginger Wright. I am the Chief Cyber Informed Engineering Enthusiast. And Ben Lampe, my colleague, is with me. Say hi, Ben.
Hi everyone. As Ginger, I am her underling to support the wonderful work we're doing with cyber informed engineering.
So, with an introduction for those who have not heard of cyber informed engineering, and again, stay far away from me because you'll hear about it if you're within my vicinity at all. This takes traditional cybersecurity, but looks at it through the lens of an engineer. Often with critical infrastructure, the processes, the systems, the outcomes that we're trying to secure exist both in the digital arena and the physical arena. And our engineers who have for years installed devices that make those processes autonomous or apply automation in those processes, they understand what are the worst things that could happen? What are the consequences if something happened in that process that would make our company go out of business, that would harm the public, that would make it so our product wasn't available anymore? And often when we think about cybersecurity, we're so focused in the digital world, the confidentiality, integrity, and availability of information that we forget about that physical world so closely attuned to it that the digital technology is controlling. So, cyber informed engineering lets an engineer put in those priorities that come from the knowledge of the process and the knowledge of the systems that perform the process and help us prioritize how we're applying cybersecurity and adding engineered controls that really prevent an adversary from creating those most harmful consequences. Ben, would you like to say more about it?
Yeah, and to build on that, you see that what we're introducing is really an extension of what organizations have available when thinking about how they're responding to digital risk. And I say it very plainly to say, don't just treat cyber against cyber because we live in a cyber physical reality, especially with our control systems. Our response plans, our control schemes can benefit from a cyber physical response, not just a cyber against cyber response.
How long does the CIE project go back?
So we began cyber informed engineering actually in 2017 or 2018. We wrote a very immature document about applying this specifically in light water reactor plants. As digitization began to come into light water reactor plants, we felt like they had the best advantage because they were so used to engineered systems. As long as they kept some of the abilities to manually control those processes, the introduction of digitization wouldn't affect their ability to be safe or responsive to the process. And then since then, in 2020, Congress directed the Department of Energy to create a cyber informed engineering strategy. And they brought a group together to think about what would it mean if we had engineers actively involved in the cybersecurity of critical infrastructure. What would they do? And then how should the Department of Energy make that information available to the public? What should DOE focus on? So, out of that, in 2022, they published a cyber informed engineering strategy that had instructions for the Department of Energy about how to implement this program and described what this group of wonderful security thinkers thought was important. They told us raise awareness. No one thinks about calling an engineer for a cybersecurity planning endeavor. We always call the cybersecurity people because that's how we think and that's what our standards say. They said that we need to get this into education so that engineers that are graduating from accredited universities understand how to be properly suspicious of digital technology in terms of its ability to add to engineering risk and not to become cyber experts themselves, but to ask the questions of others who are about how cyber accidents or cyber incidents can affect processes that they depend on. They then said, go create tools to make this easier because the national labs are really good at doing a lot of the big thinking, but the easy button is often out of our grasp. So they deliberately told us make tools, make it easier, make it something that people can understand, and then go apply it. apply it to the critical infrastructure that's in place now, but also to that new infrastructure that DOE may be thinking about. Whatever the next generation reactor project should be, it should have cyber-informed engineering cooked into it from the very, very beginning of the research phase. And so Ben and I have been working on that direction since that strategy was published.
What is the relationship between CIE and Secure by Design as far as terminology goes?
So, Secure by Design is an effort to ensure that the digital products that we produce are made to be as resistant to cyber attack as possible. And that means using secure coding standards. It means keeping component infrastructures up to date. It means really being intentional as a product creator about the creation of the product and the security implications of those decisions. Where cyber-informed engineering is different is I want secure technology. I want to buy secure technology that's made secure, but often when I'm an asset owner and I've got a power plant that's depending upon this critical software, the vendor is only responsible for what their product can do. I have a shared responsibility with that vendor to incorporate their product in a secure way and to build defenses around it to ensure that there isn't a consequence an adversary could enact through that product that would have a bad impact for me. So where Secure by Design looks largely at product creation and the vendor's responsibility, cyber-informed engineering looks at this through a lens of a shared responsibility model, where yes, the vendor should be making the most secure products possible, but the asset owner ultimately owns the consequences for those worst case scenarios and may have to buttress the security of the products they buy with additional protections. Ben, did I miss anything there?
You can start to see how CIE really helps deliver the resilience side of this conversation, where Secure by Design is that preventative measure, where you're just trying to outright prevent the situation from occurring. But given the assumption that the situation can occur, what can we do to control that resilient outcome? And that's an engineering problem, and that often benefits from your understanding of the physical side of this equation. I think also the other point that I like to throw in is it's always good until it's not good. And what I mean by that is it takes oftentimes a misconfiguration or a 0 day to often bypass the countermeasures we implement from that Secure by Design mindset. And so in that, it helps kind of demonstrate that both are necessary to truly deliver kind of the cyber resilience that has become kind of the hot term these days, as kind of why we're doing what we're doing and why the organization requires both the cyber professional and the engineer in a successful organizational and organizational, I'm getting a little creative in my language, demonstrates a strong maturity to this problem.
Do you guys have a example? I'd like to bring maybe people who aren't familiar with the term in this body of work straight into something like, well, what do they mean by this? Like an example of, look, this isn't a cybersecurity staff or person or technology. We're going to engineer out a risk. Now, it's a risk that somebody coming in as a cyber threat, risk, threat actor might try to take advantage or be able to cause something to happen. We're going to engineer that risk out. What would be an example of that?
So Ben, I'm going to turn this question over to you. You've created a database with 62,000 examples, and I saw you looking at one this morning that I wondered if you'd want to tell us about.
Sure. And just because I'm an engineer, I'll say it's 62,473 to be exact, but who's counting?
Wow,
Really?
I love it.
More to come, where we're currently stewarding a potential version 3, where we're trying to go deeper than taxonomy currently exists. So more to come on that, but getting to an example directly. Oftentimes when you think about the use of digital technology like a PLC to control the actuation of any asset, whether it's a pump or a motor or a turbine, one of the things that we need to be sensitive to is the fact that an on-off command can operate at machine speed through that use of digital technology. And in there, we have a number of different techniques, whether you can use some engineered controls within the asset, like some type of thermal relay, a thermocouple type apparatus inside of a motor to kind of disconnect when thermal activity rises to a certain threshold. The challenge there is sometimes when that stuff blows, you have to replace it. And the question now is how easily can that be replaced? The kind of that mean time to repair component, which is a very noticeable conversation there. So one of the things we always talk about is what can you do from a systematic level to help control that outcome where an adversary is able to allow the digital technology or manipulate the digital technology to operate at a speed that was never commissioned for. And that's where we've always, in a booster pump station dynamic, introduced a time delay component that sits in the analog space, the physical space, to really slow down and ensure the system stays within the operational processes, both from a procedure standpoint, but just from a commissioning standpoint. That's always held true, even if the adversary has gotten to a place in the system where they can invoke that kind of machine speed dynamic. The one that Ginger was alluding to earlier is part of our design pattern work. I'm developing an example around a turbine control, where the turbine control is given the command to just give full power, but full power is too much power for the situation that turbine is installed. So I'm using a tachometer, which is really an acceleration sensor, in combination with some switch thresholds in the electronic circuit. And without kind of going too deep, just for time's sake, that threshold allows the turbine to trip off to ensure that from a protection of safety, we don't suffer from a common mode failure, because our original solution used digital technology to trip that signal. So you can see we're bringing that functional safety perspective and kind of ensuring that we're really targeting the fact that as we introduce more and more digital technology, we're not reintroducing common mode failures as part of our functional safety certifications and kind of safety levels that we're certifying a given system to uphold and operate to.
On our March 18th conversation, we also went through an example that had a water plant moving some control software into the cloud. And their concern was that even with all the great security in place, if an adversary got in and turned the water pumps on and off and on and off and on and off, that could cause damage to the pump and potentially an 18-month outage. And in this case, something as simple as a time delay relay, think about it as a kitchen timer for commands that holds a command until the amount of time has passed and then will allow another command to go through. That would throttle what an adversary could do. So even though they could turn the pump on or off, it slows them down enough to make sure that the damage doesn't occur and that our incident response team can get out and fix the problem, even though the adversary is active in the system. So those are two good examples.
That's an elegant example because it's that's what's driving all this is we need to be able to get to that and turn it off from over here remotely. That solution doesn't cut that off. It just says, hey, as long as we're on the same page, do you need to turn it on and off every millisecond? No, we don't. Okay, let's agree on a time. You still achieve your mission, but we've now completely eliminated this particular risk because it's now just not possible, and you didn't need that functionality anyway, or undocumented functionality.
Right. And even
Yeah.
if it's an intern that I'm worried about instead of an adversary, someone who just doesn't know any better and clicks the buttons on and off, I'm
Yeah.
protected against them too. Or if it was AI and somehow an undesired autonomy started having AI issue commands to the system that could put it in that danger zone, this prevents that AI from doing it as well.
We're protecting against risk, not cyber attackers. That's way too specific, right?
That's right. We want to eliminate undesired consequences from happening. So we're trying to control risk. If you break it down, is probability times impact. So probability being the chance that I can get to the right place to do something, and then impact, the consequence of what I do. So what traditional cybersecurity does is it really acts on probability. It puts the equivalent of an obstacle course in front of the adversary. Okay, now if you want to get in my system, you have to climb this mountain and swim through this lake and get through the pit of fire or whatever the obstacles are so that you can get to a point to have an impact. With cyber-informed engineering, okay, you've got to that place, you're about to unleash that impact, and no, nothing happens. There is no earth-shattering kaboom. We've engineered out even your chance at success. So at that point, the adversary trudges home defeated, and everybody on our side is happy about that.